We're going to go through the Combined Science Foundation Level Chemistry Paper 2 today. The first question is all about the Earth's atmosphere. Now, first question, Earth's atmosphere contains 21% oxygen. We need to draw or complete the bar chart for oxygen. Now, this should be one of the easiest marks you're going to get, but there is a bit of a catch, so be careful with how far you draw your bar. If you look at the y-axis, 20% is covered by 10 small squares. So each small square is worth 2%. So when you're drawing your bar, it should be just above the 20% line and halfway to the next square. You need to be very accurate when you're plotting this bar chart. And there's our easy mark. And then the second question, what is used to test for oxygen gas? Now, again, we're just going to tick the correct answer here. And this is tricky because you just need to know your gas tests. The 4 possible answers are the 4 tests that you need to know about. So if you remember, the bottom one, lime water, is our test for carbon dioxide. Damp litmus paper, our test for chlorine. Now, it comes down to the burning side of things. Remember, a burning splint is how we test for hydrogen. That's our squeaky pop test. So it means that the correct answer is our glowing splint. Remember, oxygen will relight a glowing splint. Now, we've got some information about the early Earth's atmosphere and the atmosphere as it is today. So you've got 2 pie charts which is comparing the data. Now, 1.3 is quite a wordy question because it's actually asking you just to complete the 2 sentences. You're given the options of what words to use, which makes life a little bit easier. So since the Earth's early atmosphere, the percentage of nitrogen in the Earth's atmosphere has done what? Well, if you look at the left-hand pie chart, Earth's early atmosphere, there were small amounts of nitrogen. In the Earth's atmosphere today, we've got 78% nitrogen. Clearly, nitrogen has increased. That's that one done. And then the second part, since the Earth's early atmosphere, the percentage of oxygen in the Earth's atmosphere has done what? Well, again, if you look at the early atmosphere, there isn't any oxygen. So there's absolutely none there. And now we have 21% oxygen. So again, that has increased as well. Don't get too worried about using the same word twice. Okay, and then 1.4, the Earth's atmosphere today contains a small amount of carbon dioxide. We're being asked why has the percentage of carbon dioxide decreased since the Earth's early atmosphere, and we need to tick 2 boxes. Now, here we can get rid of 3 of the answers because they actually increase the amount of carbon dioxide. So if it starts at the bottom, volcanic activity, well that produces a lot of carbon dioxide gas. Respiration, when we breathe out a lot of CO2, so that's going to increase the amount of carbon dioxide. Industrialization, this is getting at the fact that we're burning lots of fossil fuels and producing carbon dioxide. So those 3 answers are clearly incorrect, and it means that there is a lot of carbon dioxide dissolved in water and in the oceans, and also lots of carbon gets locked up in the formation of sedimentary rocks. So there's your 2 correct answers. Now again, we've got more data to look at, and we're looking at the concentration of nitrogen oxides in a city from 7 o'clock in the morning till 6 o'clock at night. The question also tells us, and this will help us later in the question, that these oxides of nitrogen are produced when nitrogen reacts in a car engine. So 1.5, which 2 times have the highest concentrations of oxides of nitrogen in the atmosphere? Well, we're looking at these 2 peaks. You can see, drop down to the x-axis, our first peak is at 9 o'clock in the morning, and then the second peak is at 5 o'clock in the afternoon. There's our 2 correct answers, and there's 2 marks. Now, suggest why there are the highest concentrations of oxides of nitrogen at these times. So if you think about it, you've got earlyish morning, you got late afternoon. That's generally when the rush hour is, and you've got a lot of cars, buses and lorries on the road. Because nitrogen oxides are produced by car engines, that's where your nitrogen oxides are coming from. So you've got rush hour, you've got a big increase in cars, lorries and buses on the roads. Now that question's out of 9 marks, hopefully you got 9 out of 9. Question 2, the question's about fuels. Now, coal deposits were formed from the remains of trees. Name the process in the leaves of trees that uses carbon dioxide. Right, so this is linking to biology, and there's only one possible answer there. We're looking at photosynthesis, process by which leaves take in carbon dioxide and water and make glucose and oxygen. So, nice easy mark there. Now the question is, how is coal formed after trees die? Well, certainly not by burning trees. Trees, as far as I've ever seen, definitely don't melt. So the only real answer there is that trees get compressed. Get compressed by layers of rock forming above them and gradually crushing them, and over millions of years turn into coal. Now coal is quite an unpleasant material because it contains small amounts of sulfur. We need to name the gas produced when sulfur burns in oxygen. Well, we're basically oxidizing sulfur. So we're actually producing a gas called sulfur oxide, better known as sulfur dioxide. Now, give 2 problems that sulfur dioxide causes. Well, a big one, it's not so much of a problem as it used to be, was acid rain. How the gas escapes into the clouds, and when it basically dissolves into the cloud, and it forms a weakly acidic solution, and then it rains down a weak acid, and that's bad for plants and rivers and so on. You've got acid rain there, but you've also got respiratory problems, or basic breathing problems. So it's a very unpleasant gas to breathe in. If you've got things like asthma, it's particularly dangerous for you. Right, and then 2.5, we've got more data analysis here. So we're looking at the relative amounts of electricity generated from different fuel sources in the UK from 2012 to 2018. Now we've been asked to describe what happens to the amounts of fuels used to generate electricity across that time. Now this question is worth 3 marks, so you need to be thinking about making at least 3 points to be able to try and get those marks. Now there's 4 different types of fuels, or groups of fuels. So if you look at the fossil fuels, in 2012 it's way up here, 2018 it's down there. So the first observation is that the use of fossil fuels has gone down. We then look at the unshaded section, which are renewable fuels, and you can see that that is getting bigger every time. So our use of renewable fuels is increasing. Now if you look at nuclear fuel, that box is about the same size every time. So it means that the nuclear fuels haven't changed. So nuclear fuel, and then the final category, the others, that doesn't seem to have changed over the 6-year period either. So you just need to make 3 out of 4 of those points and you'll get you 3 marks. So that question is out of 8. Again, well done, you've got all 8 marks. Now question 3 is all about ammonia and its compounds. Now here we've got students heating a sample of ammonium chloride, and the equation for the reaction is ammonium chloride reacting to form ammonia and HCl. What's the name of the product with the formula HCl? Well, it's made out of hydrogen and chlorine, so we call it hydrogen chloride. Now I think this might be the easiest mark you're likely to get in this exam paper. It tells us that ammonia is a gas. what is the state symbol for ammonia? Well, G for gas. That's our option. 3.3, how does the equation show that the reaction is reversible? Well, that is our sign. If the reaction just went in one direction, we normally draw an arrow. All you need to do is, that tells us that this reaction is reversible. I don't know whether to give you so much space to answer that. Just by writing that, you'll get the mark. And then 3.4, you need to complete the sentence. The forward reaction is endothermic, so the reverse reaction is what? Well, if the forward reaction is endothermic, the reverse reaction has to be the opposite. Exothermic is our only option in this case. And then question 3.5, complete the sentence. Again, we're given the words to help us. Equilibrium is reached when the forward and reverse reactions happen at exactly what? Now, the correct answer here is rate. So, as fast as the forward reaction is happening, it is matched by the rate of the backward reaction, the reverse reaction. Concentration and temperature will both have an effect on the equilibrium position. So the one that we're looking for that stays the same will be rate. And then we're looking at the use of catalysts. Catalysts are used to make ammonia. We've got our energy profile diagram, and we need to work out which letter represents the activation energy for the reaction with a catalyst. Now there's a couple of the answers we can get rid of straight away. Now this is clearly an exothermic reaction because our products are at a lower level than our reactants. Now that A is the energy that's released, energy given off, so it's definitely not that. Now B seems to cover some of the energy given out, but also the activation energy, so it's clearly not going to be that one. So we're left with C or D. Now the advantage of using a catalyst is that it reduces the amount of activation energy needed. Therefore, we're looking at C, the smaller increase in energy. So again, just need to recognise that diagram. C is our correct answer. Then 3.7, give one reason why using a catalyst reduces costs, but don't answer in terms of activation energy. Well, if we use a catalyst increases the rate of a reaction, so we're going to produce our product quicker. Now it says don't talk about activation energy, but you can talk about the fact that less energy is required to produce our product. Or you could state that a lower temperature can be used, which is linked to less energy required. But any of those three answers would get you a mark. Now 3.8, ammonia is in a mixture that is used as a household cleaner. What is a mixture that has been designed as a useful product called? This is just one of those definitions you just have to remember. It is called a formulation, and that's the only acceptable answer there. That question's out of 8, so hopefully you got 8 out of 8. Now question 4 is all about rates of reaction, and it's looking at the effect of concentration on the rate of reaction between sodium thiosulfate solution and hydrochloric acid. This is our disappearing cross experiment. Now, if you read through it, you've got the diagram of the apparatus, you've got the method there. Now, step 5 is important because this is going to tell us some useful information. We need to repeat the experiment with different concentrations of sodium thiosulfate solution. Now, different suggests that we're changing the concentration of sodium thiosulfate solution. Like I said, that will help us with the next question with variables. We need to pick out what is our dependent variable, what is our independent variable. So remember, don't mess in class. Don't mess, dependent is measure, independent is what we change. Hopefully we've already established we've got different concentrations of sodium thiosulfate solution. That is the thing that we're changing. So the independent variable is that top box, the concentration of sodium thiosulfate solution. Now what's the dependent variable? Well, it's the thing that we're measuring. So that's going to be the time taken for the cross to no longer be seen. It's really important that you can pick out the variables from all the different types of investigation, because these are easy marks when you get your head around them. Right, next one. This is just reading the temperature off a scale. Now you can see that your answer is going to be somewhere between 19 and 20 degrees centigrade, but it's clearly less than 20, so it's going to start with 19, and then we need to look at these little lines. You've got 10 small lines, so we're splitting this up into 0.1 degrees centigrade. This is halfway up, 5 little dashes between 19 and 20 means that our answer is 19.5 degrees centigrade. And then 4.3. Here we've got, well again, these should be straightforward marks. We've got to plot a graph. So we're going to get the first 2 marks just for plotting the numbers accurately. Now it's much easier for you to plot them on your graph paper. Now I'm going to try and do it, and the only catch here again is look at this y-axis. We've got 10 squares, 10 small squares, which covers 20 seconds. So each small square represents 2 seconds. So our first number is 82. So it's one small square above 80. 0.2 is a bit easier because it's dead on 40. And then 0.3 is on 20. And then 0.4 is 13. So that's 1.5 squares above that one. And then we're on 10, then 8 seconds. Now when you look at those data points, it's clear that this is going to be a curved line of best fit. Now you need to do this freehand and make it as smooth as possible going through all the points. Don't be tempted to get your ruler out and do a dot to dot. You will automatically lose that point, that mark, for drawing your line of best fit. But even if it's a little bit shaky, that's absolutely fine. And that will give us all 3 marks. Now, the next question is asking us to predict the time taken for the cross to no longer be seen with a concentration of 0.7 molar solution, which is right here. So you would draw a cross to the y-axis, and I reckon that comes out as being 7 seconds. So when it's asking you to choose the graph, that's exactly what you need to do with it. So like I said, you've got that question, which we've already used the graph to work it out. You're looking around 7 seconds. If you've got somewhere between 6 and 8, that would be acceptable. You'd get the mark. And then 4.5, you've got to complete the sentence. So as the concentration of sodium thiosulfate solution increases, the time taken for the cross to no longer be seen while the time goes down. So it means that that is decreasing, decreases or goes down. Right, and then 4.6. Again, this one you should look at being straightforward because it's 2 marks for a math style question where they give you the equation. So we need to work out, it's asking us calculate the mean rate of the reaction. We're given the mass of sulfur that's produced, and we're given a time. Substitute the numbers we've got. Well, we don't know the rate. Rate equals 0.725 divided by our 20 seconds. Put those numbers carefully into your calculator, and you're going to get 0.03625. And the next question is asking us about the units. Now, the thing to remember is that a rate of reaction is a rate. It's per unit time. So we should always be, it should be something per second, something per minute, something per hour. So when you look at your possibilities, there's only one that really stands out. But the way to also think about it, make sure you get the right answer, you've divided grams by time. So you got those grams divided by the seconds. G/S, that is our correct answer. And then another maths question. This is where we need to work out a mean value from the table of results. Now, it's saying do not include the anomalous results in your calculation. So they've given you a bit of a clue here. Now, it's important to remember what the anomalous results kind of actually means, and that's one that doesn't fit the pattern. This is why we repeat tests, help us identify anomalous results. Here you can see you've got three numbers around about 60 odd, you've got a number at 82.3. That clearly does not fit the pattern. So that is our anomalous results, so we discount it when we calculate our mean value. So we now work out the mean equals 60.5 plus 63.2 plus 65.7. Put that in your brackets and we divide it by 3. Put that carefully in your calculator, be particularly careful with your brackets, and that will give you an answer of 63.133 recurring. Now this is when you need to go back and check the question. Give your answer to 3 significant figures. Well, that's worth an extra point, an extra mark. So we now need to look at 63.1333 recurring. So if you look at the first 3 figures, 63.1, well, we need to look at the 4th figure now. If that's 5 or more, we round up. If it's less than 5, we round down. Well, clearly 3 is less than 5, therefore we round down. So we get the 3rd mark in this question by doing the rounding, and the answer is 63.1 seconds. Now that question is out of 14. Well done if you got 14 out of 14. So in question 5, this question is all about hydrocarbons, and figure 9 shows you an example of a hydrocarbon. The first question is you need to complete the formula for the hydrocarbon shown above. Now this should be a relatively straightforward question. You just need to count up the number of carbons, count up the number of hydrogens, then fill in the blanks. We have 3 carbons, and then it's just a case of counting up the number of hydrogens, and you've got the 8 hydrogens. Now, you need to name that hydrocarbon. So if there's 3 carbons in the chain, we're starting with pro, and it's an alkane, so you're looking at propane. You just need to remember the names of the first 4 hydrocarbons. Which homologous series does the hydrocarbon belong to? Now, a homologous series is just what group. How do we band them all together? These are all examples of alkanes. So that's your series. Question 5.4. We've got 30 grams of another hydrocarbon, contains 24 grams of carbon. We've got a calculation, or we need to tick the box of which is the correct way to calculate the percentage of carbon in the hydrocarbon. So here, to work out that, you would want to know the mass of carbon, and you would divide that by the mass of the hydrocarbon. So that would give you the fraction, but you'd want to turn it into a percentage. So you'd multiply that by 100. Now, if we substitute the numbers in that we've got 24 multiplied by 100, and we divide all that by the mass, which is 30. Now I just need to look across and find the answer, which is correct, which is the 3rd box along. Question 5.5. We've got some boiling points of various hydrocarbons, and you need to describe how the boiling points change as the number of carbon atoms in the hydrocarbon increases. So what is happening to the boiling point as the chain length, the number of carbons changes? Well, best bet here is if you look down the table, starting off at a chain of 2 carbons, then 4, 6, 8 and 10. So the carbon chain length is increasing. And then you look at the boiling points. We start off at minus 89, then we're going through 0, and then the temperature is gradually increasing. So the temperature is also increasing. So how do we describe this? So as the number of carbons in the hydrocarbon increases, so does the boiling point. And there's your mark. Okay, so now we're looking at cracking. 5.6. Give one condition that could be used to crack hydrocarbons. Generally with most kind of reactions, if in doubt, always go for a catalyst and a high temperature. If you said either of those two things, a catalyst and a high temperature, you would get the mark. When we talk about a high temperature, we're talking somewhere between 400 and 900 degrees centigrade, but just saying a high temperature is suitable. The other acceptable answer here would be increased pressure, and that leads to the breaking up of our hydrocarbon. And then the next question is we need to balance the equation for the cracking of C6H14. Now here, again, this just comes down to being able to do a little bit of maths. We're starting off with 6 carbons and 14 hydrogens. Remember, we have to use up all of those atoms. Now, on the right-hand side, we've got ethane forming. That's C2H6. And then we also get ethene forming. Remember, in cracking, you always get an alkane and at least one alkene forming. Now, we've accounted for the ethane, so we need to take 2 from the 6 carbons. So we've got 4 carbons left. We take the 6 from the 14, and that leaves us with 8 hydrogens. Now, if we look at the formula for ethene, it's C2H4. Well, the only number we can put in here to balance this would be a 2. So we now have the same number of carbons and hydrogens on the left as we do on the right. 5.8. Give one reason why hydrocarbons are cracked. It's to make the chains shorter, to make smaller molecules which can be used as fuels. Long chain hydrocarbons aren't as useful, therefore we need to break them up, and like I said, it's to make smaller molecules, or you could talk about to produce fuels. Either answer will get you the mark. Okay, now window frames can be manufactured from wood or plastic. Unfortunately, the table here has been taken out of the question, which makes carrying out the with not having the life cycle assessment information in front of you, it makes it quite difficult to actually answer this question. Now, the advantage of using wood, and like I said, this would be so much easier if you actually had the table of data in front of you. Making wooden window frames uses less energy, uses less coal. I think without that table that would be virtually impossible to get. So again, that's linked to the energy, and also produces less waste. And the other advantage of wood, which you probably know this already, so a fourth possibility is that wood is a renewable resource. Obviously wood literally grows on trees. That question's out of 11. If you struggled on that question, it's understandable. There's no table of data there. It does make it quite tricky. So question 6 is all about chromatography, and we're investigating some brown ink. Here we've got the diagram of the apparatus used, and you can see that we are carrying out chromatography on the brown ink, and we're also running samples of yellow, green, blue and red alongside our sample. Now, this is quite a common question. We need to give 2 errors which have been made by the students. Now, there's at least 2 glaring errors here. Now, the first one, and this is quite a common mistake to make, is that the start line has been drawn in ink. So the start line in ink. What's the problem with that? Well, of course, you're carrying out chromatography on ink samples, so there's a possibility that the ink in the start line is going to mix with the actual sample of ink. So the start line ink will mix with the samples, which is obviously going to interfere with the chromatogram that you get. The other one is our solvent line. Our solvent line is above the start line. So the solvent above the start line. Remember, in chromatography, you need the solvent to be below the start line, somewhere down here, because what happens is the water, the solvent, gets absorbed through the paper, and the solvent moves up through the paper, and as it gets to the sample of ink, it dissolves that ink, and then it carries the dot depending on how soluble the ink is. The higher the ink moves, the more soluble it is. The lower it is, the less soluble. Here, what's the problem going to be? Well, you're just going to wash the samples off your paper. So the colours or the inks will dissolve in the solvents, and you won't get any chromatography happening. You'll just get some coloured water. Now, there is a third error. There's no lid on the chromatography tank. What's the downside of that? It means that our solvent, the problem could be the solvent could evaporate. Now, if you're using water as a solvent, it's probably not that likely to happen, but if you're using something like ethanol or other more volatile solvents, that's a possibility. So the third acceptable error would be the lack of a lid. Right, so now we've got a student has actually carried out the investigation correctly, and we've got our results, which is shown in figure 11. Now, with this, we're going to have to analyse the chromatogram, and quite a good way to do it is to get your ruler, and it's going to be much easier for you because you'll be using a ruler, is if you look at the brown ink, which is the ink that we're analysing, and just draw lines across and see where you've got matching kind of dots in your sample. Right, so we've got to give 2 conclusions the student can make about the 4 colours in the brown ink. The first, well, theoretically this is 3 separate conclusions. You could say brown ink contains, well, if you look, contains red, it contains yellow, and it also contains blue ink. So they're all possible conclusions. Now, we've got this dot here where we don't know what colour that is. So it means that our brown ink contains an unknown colour. And that's the only thing we can conclude from that. You could also conclude that the brown ink doesn't contain green ink. So there's no green ink in brown. You could also say that the blue ink is most soluble, because if you look at the chromatogram, it's risen quite a way to the top. And at the same time, you could say that the red ink is least soluble. So there's lots of possibilities that you could get there. You're only going to get a maximum of 2 marks, so you just need to give 2 conclusions. Right, now 6.3, why was the green colour still on the start line at the end of the experiment? Now generally this chromatography is all about the solubility of the ink sample in that solvent. Let's have a look at the possible answers. The experiment was left for too long. Right, well that's definitely not the case. Then the green colour was insoluble in the solvents. That is going to be our possibility. The green spot contained too many colours. Well, we didn't get any separation, so that's a load of rubbish. The green spot was too small. Well, if you look at the chromatogram, all the samples, all the spots were the same size, so that is just nonsense as well. So it gives us our only possible answer, which is the green colour was insoluble in the solvent. Now 6.4, we've got a bit of a maths question, and this is looking at our RF value. So that's our retention factor, and we're given that as 0.24. Now the colour moved 1.8 centimetres from the start line. So we've got some data here. So we've got the RF value, you've got the colour moved 1.8 centimetres. Now we're even given the equation for the RF value. Now your first mark is just going to be for substituting in your numbers correctly. We're given the RF value of 0.24. Distance moved by colour, that is 1.8 centimetres, and we're going to work out what's the distance moved by the solvent. That will be x. We just get a mark for putting numbers in like that. We get our second mark for being able to make x the subject of the formula. So we end up with 1.8 divided by 0.24. Now input those numbers carefully into your calculator and you will get an answer of 7.5 centimetres. This is where you do your common sense check. That seems quite reasonable. The solvent will always travel further than the colour. That seems like a reasonable answer. Now that whole question was out of a maximum of 10 marks, so well done if you got 10 out of 10. Alright, question 7. Water that is safe to drink is called potable water. Compare how easily potable water can be obtained from wastewater, that's from sewage, and from groundwater, which is fresh water. Now this is a 6 mark question, and there's lots of information you can put in here. Now because there's a key word here, you're comparing how easy it is to get drinking water from these two sources. Now a comparison, you need to be comparing things, so this question is set up nicely to answer with a table. And I would have a bullet pointed table, and it's a good way to get the full marks rather than writing kind of a whole load of a couple of paragraphs about it. It's much easier to do a comparison, like I said, using the format of a table. So we've got groundwater against wastewater. Now, and we're just comparing it. Now, first of all, it's much easier to obtain drinking water from groundwater. It's a lot purer, so easier to obtain. Now, in comparison, remember we're comparing, it's more difficult to obtain. So remember, don't just talk about one in isolation. You've got to be making a comparison. To purify or to form our potable water, make it clean enough to drink, there's fewer processes with groundwater. So it means that with wastewater, there are more processes. Because there's fewer processes for groundwater, it takes less time. So it means that wastewater takes more time. Now, with our groundwater, we need to filter through filter beds, and that removes the insoluble particles. So it's filtered in filter beds to remove insoluble particles. Now, with wastewater, because the water is just generally dirtier, the screening and grit removal. So we're taking some of the bigger chunks out here, and that removes the larger kind of particles. You really don't want lumpy drinking water. So got quite a few points here already, but then the other process involved is you need to use sedimentation, allowing the finer particles to settle, and that produces sedimentation to produce our sewage sludge and effluent. So that's again waste material. You really don't want that in your drinking water. And then you need to carry out aerobic treatment, and this is generally with bacteria, of the effluent. And that reduces the solid waste. So you can see already there's a lot more processes going into making the wastewater cleaner, and we still haven't finished. So the groundwater is sterilised, and normally we can use chlorine to do that, low concentration. We might use ozone, or we might use UV light, and that kills the bacteria. At this point, our groundwater is going to be safe to drink. Now, with wastewater, we also need to digest the sludge anaerobically, so we're using bacteria again to help us. So that's by bacteria, and that removes the organic material. Now, there's quite a lot to cover in all that, but if you make most of those points, you should get the full kind of 6 marks on it. In terms of the mark scheme, there's only actually 2 levels of answer here. So if you just made some, identified some of the features, and 1 or 2 of the difference noted, you can only get a maximum of 3 marks. Now, to get the full, anywhere between 4 and 6 marks at level 2 answer, you need to be making sure that you're making it abundantly clear where the similarities and differences are. So, here we need to be using, like we have done, language like easier as opposed to more difficult. So it's clear that we're making a comparison. Fewer processes compare with more processes. So make sure the language we're using is showing that we're clearly comparing the 2 different types of source. Well done if you got 6 marks out of that one. It's one of the trickier 6 mark questions you're going to get. Right, and then scientists produced potable water from 150 cubic centimetres of salty water. Which process can be used to produce potable water from salty water? Right, so you've got a salt solution. How do we get water? If we look down sterilisation, well, that's not really going to help because the salt is still going to be in the water. Salt is soluble, so filtration's not going to work. Electrolysis is definitely going to work using electricity. We're just going to be splitting up some of the materials within there. Distillation. We heat up the salty water, boil the water, and then condense the steam back into pure water. We call it distilled water because we use distillation. And then finally, we're going to finish off with a maths question. Our salty water contains sodium chloride. The scientists collected 2.4 grams of sodium chloride from 150 cubic centimeters of salty water. Calculate the concentration of sodium chloride in grams per decimeter cubed. So let's just highlight the information. We've got 2.4 grams of sodium chloride in 150 cubic centimeters of the salty water. So we've got 2.4 grams in 150 cubic centimeters of water. Now, this is where we need to be converting our 150 cubic centimeters into decimeters cubed, because we need to calculate the concentration in the number of grams per decimeter cubed. This is where you need to remember that 1 decimeter cubed equals 1,000 cubic centimeters. This is where your prefixes come in handy. Decimeter. Deci is 10. 10 times 10 times 10 gives you 1,000. That's where the 1,000 cubic centimeters comes from. So our 150 cubic centimeters, to convert that into decimeters cubed, we need to divide by 1,000. So we end up with 0.150 decimeters cubed. We can now work out the concentration from this. So if we've got 2.4 grams in 0.15 decimeter cubed, it means to calculate the concentration, we then need to do the mass. We've got 2.4 divided by the amount of liquid solvent in decimeters cubed. We've got 2.4 divided by 0.15. Put that into your calculator carefully and you get your answer of 16 grams per decimeter cubed. And this is where your common sense check needs to come into it. 150 cubic centimeters is about a sixth or a seventh of a decimeter cubed. If you multiply 2.5 by 6 or 7, you're getting around about that answer. So always have a common sense check. Does your answer look sensible? In this case it does. Right, you're now at the end of the paper. That question was out of 10 marks. The whole paper is out of 70. Add up your score and well done if you got 70 out of 70.